false theorem. Are there any questions about the statement of false theorem or the proof that we saw so far? There was one question posed by one of the students, which we'll clarify today. But are there any major issues? The statement at least. So what we are given is a bipartite graph. It has two partitions, U and V. And you know that you assume that the set U is the smaller partition. So U has fewer vertices than V. Like the one example here, there is U here, there is W here. So the two partitions are U and W. And you want to find a matching that saturates every vertex in the smaller set. Right? So essentially what you want to do is find a set of vertex disjoint edges that saturate every vertex in the set. And what Hall's theorem says is essentially this set here. This is what blocks you from getting a match. So if there is a set where the neighborhood of the set has fewer vertices than the set itself, then it's not possible to find a match. A matching that saturates every vertex in it. And this condition is called the Hall's condition. So the statement that we want to prove is the bipartite graph G contains a matching of size U if and only if G satisfies Hall's condition. So one direction is easy, that if G has a matching of size U, the cardinality of the set U, then G satisfies Hall's condition. So what we wanted to show the other day was the other direction, right? So you know that you assume that G satisfies Hall's condition. And we want to show that no matter what subset of the smaller set you choose, if you look at its neighbors in G, the cardinality of that set will always be greater than or equal to the cardinality of the set S. Right? So Ng of S is the neighbor of every vertex in the set S in the graph G. So for this, we actually used strong induction. So there is one confusion there. So let's clarify that. So what do we mean by strong induction on the size of U? This means that you assume for all cases module less than K, and then you try to prove for module equal to K. Right? So for U, when there's just one vertex in the smaller partition, you have definitely one edge, and you just pick that edge because we know that G satisfies Hall's condition. Now in the other case, you assume that the statement is true for all U less than K. For all bipartite graphs, where the smaller partition has strictly less than K cardinality. The cardinality of the smaller partition is strictly less than K. In that case, whenever such a graph satisfies Hall's condition, so let's put the graph, name the graph G hat. Okay? So if G hat satisfies Hall's condition, then G hat has a matching of size matches every vertex in the smaller partition, which is U. So let's say that I should also mention here. So here, let's just assume that U hat is the smaller partition. Oh, okay, it's written here. This one. Okay, so there was one question that was posed at the end of the lecture. So let's see. So what did we try to show? How did the proof proceed? You want to somehow get into the inductive hypothesis, right? So an induction step, you know that the cardinality is related because if it's one, you can use the base. So, and you know that G should have a name called U, and we pick this vertex, this H in the matching, this UW, and then inducted on the remaining graph. And we call this graph H. So there are two cases, either that H satisfies Hall's condition or H does not satisfy Hall's condition. If H satisfies Hall's condition, we are actually very lucky because by the inductive hypothesis, now you remove U, right, from the smaller partition in order to produce the graph H. And you also remove W from this partition. So you reduce the size of U by 1 and the size of W by 1. So this becomes U minus 1 and this becomes W minus 1. So this still continues to remain the smaller partition. And it has strictly less than K vertices. So you must be able to find a matching in this new graph H that saturates all these vertices. Right? The ones without this vertex. Right? These vertices you should be able to find a matching. And that matching will not involve W because you remove W from the other partition. Now you use that matching and you append the edge UW to it, and this whole set, right, is vertex disjoint. and every vertex in U is saturated by this matching. So the final matching is M prime, M, which is take the edges in M prime and also add the edge U. This is when when this subgraph that you produced by removing the vertices U and W satisfies Hall's condition. But now the problem could be that it may not satisfy Hall's condition. So at least until this, is it clear? Satisfying the Hall's condition, please. If there are any questions here, then we can take. So now the case is when H does not satisfy Hall's condition. So last time what I suppose the following. So when H does not satisfy Hall's condition, right? You produce the graph H by removing the vertex U and removing the vertex W. Right? And you know that this graph does not satisfy Hall's condition. So now what you have to do is you have to produce a matching in the graph G that saturates all of you. The only clue that you have is it does not satisfy Hall's condition. So now what we will actually do is we will produce two subgraphs. Okay? Let's call this F1 and F2. So this subgraph will saturate, because you know that there is a set X, this subgraph will saturate all of X. That is, all the vertices in X will, at the end of this procedure, what you do is, all the vertices in X will be matched. But then there is another portion, right? In order to match U, you have to match a portion of X, and the remaining is U minus X. So this you will match separate, and you have to append these two matches. That's what we do. Is the idea clear? So right now, what you know is, you know that you have a subgraph H, and that graph does not satisfy Hall's condition. Right? So you look at, so when you know that the graph does not satisfy Hall's condition, what do you have? You know that there is a subset of the smaller cardinality set, such that if you look at its cardinality, it will have far more size than its neighbors, right? That is why it did not satisfy Hall's condition. Then we mean neighbors of X in the graph H. So now we want to use this set X to produce two graphs. One is F1, the other is F2. So in F1, what I will do is the following. Right? So in F1, I will consider the set X. So let me just draw a picture. So now I have, this is the set U. In this I have X. Right? So what do I know about X? X is a subset of U minus U, and it has a far more size than its neighbors. And then there is the set W. Right? This is in the graph G. Now this portion is U minus produce F2. So it will have, this will also be bipartite, but it will have incident edges like this. So I will find a matching M1 that saturates this portion. That is, it saturates all of X. So every vertex in X will be matched. And I will find another matching here, which is M2. That saturates every vertex in U minus X. So if I put together M1 and M2, I will get a match in G. Right? So I am not going to use the graph H from now on. I am just using the graph. I'm just thinking about the graph H. I know that H does not satisfy Hall's condition. So there is no point in working with H at all. The only witness I have is, I know that there is a set X in U minus U, such that if you look at its cardinality and its neighbor's cardinality, the neighbor will have more cardinality in H. Okay. So does that partially at least answer the question that we had last time? It will be more clear when we finish the paper. I think Milan had raised this question.
Yes.
Okay. So now what do you know? You know that the graph H does not satisfy Hall's condition. So you know that there is a set with this property. Now use this set to construct a subgraph of G. So what do you do is pick this set X and you pick its neighbors as the other partition. So one partition is X here. The other partition is the neighbors of X in G. And U clearly is outside this set because X is a subset of U minus U. But don't worry about this. This guy will be matched in U minus X. He will be there in U minus X. So the other graph will, F2, when we define it, will take care of it. Right now, what we want to do is we want to define a matching that saturates, find a matching that saturates all of X. So for that, we have to use inductive hypothesis. For that, what are the conditions that we should show? We should show that in this new graph, X is the smaller partition. Okay, that's the first thing. And then you have to talk about this graph F1 satisfying Hall's condition. If these two things are true, then you can use inductive hypothesis. So for the first thing, you know that X is a subset of U minus U, which is a subset of U. Right? So the cardinality definitely is less than K, and you can now use Hall's condition. Now you can use inductive hypothesis. Now you know that G satisfies Hall's condition. So its cardinality, if you look at the neighbors of X in the graph G, definitely there must have been more neighbors than the set X itself. Otherwise, G would not have satisfied Hall's condition. Right? So now you have these two things, right? One is X is the smaller partition because X is a subset of U and U was the smaller partition to begin with. And this graph F1 satisfies Hall's condition. Okay? So I should not have written here Hall's theorem. I should have written Hall's condition. What does that mean? It means that whatever set you take, it will have, you will not be able to find a set that has more cardinality than its neighbors. Hall's condition. So now you can use induction on F1, right? So this immediately will tell you that you can find a matching M1. But the only problem is this will only saturate every vertex in X. So this portion you will have covered. So you will find partners here for the vertices in X only. But what is the goal? Remember, you want to find a matching for every vertex in the set U. Right? To do that, what should you do? You must also match this portion, right? There are remaining portions in U that are not in X. So that portion we have to match. So for that, I have to now define another graph. Right? So let's define that graph F2. So what should be the first partition of F2? Let's just look at this and say. So this thing we have completed. This we have matched with a few of them here. So this essentially, if at all, what will it involve? It will involve the neighbors of X in the graph G. Only from there you can pick partners for X. Okay? These things. Now, can you tell me what the two partitions of F2 should be? What is our goal? And from that, can you just define? So this portion is done. What is the remaining portion?
U minus X.
So the first partition has to be U minus X. And what should the second partition be? So you must remember that to construct a matching, you should not reuse these vertices, right? These vertices you should not use. Otherwise, there will be two edges in the matching that are not vertex distant. They may share a vertex. So what, from where can you find matches for U minus X? So one partition is U minus X. What should the other partition be for this new graph, F2? Is this not clear? If it is not clear, we'll do it again. Even if like one of you have a doubt in this. Or if you don't understand what we are doing at all, then we'll go over this again.
W minus NGX.
What minus NGX?
W minus NGX.
So that is this portion. So these things you have already used to match vertices in X. So these things you should not use. The remaining portion is W minus the set NG of X. So any questions? So how do you write this? So F2 is G of this. What do you mean by this? So it's the subgraph induced on these two partitions. One is U minus X and the other is W minus NG of X. As the partitions. So you will look at these two vertices, these two sets, the set U minus X and the set W minus NG of X, and take the graph that contains all edges across this. So this is your new subgraph that you'll work with. This portion you have already matched, and that matching is M1. Now the goal is to find a matching M2 in, so what is the goal right now? Is find a matching M2 in which graph?
F2.
F2 that saturates U minus X. So U, if you remember, was here. W could have been here, like what last time we had talked about. That is possible. We don't care about W right now. So if W was here, you will find another neighbor for U here. Matching M2 will take care of it. If there are any questions about this, we will do it again. So please ask. I cannot figure out whether you understood it or not. Because I don't see your videos, right? So you should. So we haven't done this yet. So this portion we have to do. But that is really so this portion is really where this nice, interesting math comes up, right? Just talking about the size of sets. So you have so many sets and you know that you have to now figure out whether F2 satisfies Hall's condition. If it satisfies, what can be done? Can we construct a matching out of it and so on? But are things until now clear?
Ma'am, NGX will have the same cardinality as X, right?
Yes, we will come to that, right? That observation is correct. But are things clear so far?
So, yeah, okay, ma'am. Now it's clear. Okay.
So if you have any questions, if any one of you have any questions, please ask. Or if you need like time to digest, you can wait a couple of minutes. Okay, so now what should you do? You want to find the matching in F2 that saturates this set. So for that, I have to use the inductive hypothesis. But before that, let's try to observe how. So you have a set X, right? You started with this set X, right? You know that H does not satisfy Hall's condition. You have this set X. And you know that the cardinality of X is much larger than its neighbors in the graph H. So what do we know? You look at the set X, its cardinality is much larger than the neighbors. So this is because H does not satisfy Hall's condition. Right? But you know that G satisfies Hall's condition. So what can you say about these two quantities? What is the inequality that I must write here? Somebody else who hasn't answered so far. I don't want to recall him. Please unmute and answer. So you know that G satisfies Hall's condition. So what should be this inequality here?
Like Milan said, they have to be equal.
Well, at least you can say that it should be less than or equal. That much. But how did we go from H to G? So I'm just trying to say what Milan is trying to formalize what Milan is saying. So how did the number of neighbors change from G to H? So you just removed one vertex, right? You just removed like U from G and also W on the other side, and you just obtained H. So how could an inequality go from like strictly less than to suddenly like greater than equal to, right? The only possibility is it should have been equal in the first place. Otherwise, you cannot jump to a size difference of more than 2. Right? So this just from the way we built. So just by looking at how the number of neighbors changed, you can argue that the cardinality of X should have been equal to the cardinality of the neighbors. Is this clear to everybody? It was initially less than or equal to, and suddenly it became greater than. right? While we only removed like one vertex to go from G to H. So it should have been equal to in the first place. That is why this sudden strictly less than came into picture. So this you must keep in mind, that the picture that we initially drew, right, they are not, I don't know if I drew this. Yeah. So this and the cardinality, right, this and the cardinality of its neighbors, these two sets should have been like equal. There are no extra stuff. So this is some observation that we have, and we have to use this. So now let's go back to showing that F2 does F2 satisfy Hall's condition, or can you use inductive hypothesis on F2? That's the question. Right. So what is F2? F2 is the graph you construct from G. One partition is U minus X. The other partition is W minus NG of X. So the first thing we have to show is that this part is the smaller partition. Right. So we want to ask, what can you say about the cardinality of U minus X and the cardinality of W minus NG of X? So it's only playing around with cardinalities from now on. Right? We know that the cardinality of U is less than or equal to cardinality of W. So in the original graph given to you, U was the smaller partition. So now this is less than or equal to. Why is that the case? This is because the cardinality of X is exactly equal to the cardinality of NG of X. Is this clear? Because these two things are equal, you know that now, right now, even now, this is the smaller partition. So one job is done. Now you have to ensure that this smaller partition has cardinality. In order to use the inductive hypothesis, what should this be? Are things like super clear or super confusing? It should not be like really hard.
Less than K.
Right. So U minus, so what was X? X was a subset of U minus U. So already one vertex formed. So definitely U minus X has cardinality strictly less than U. And this one has cardinality K. So it's just strictly less than cardinality K. This is because you know that X is non. No, maybe I won't write these things. Okay. So what is the other thing that we have to show now to use inductive hypothesis? We know that this guy is a smaller partition. It has to be less than K. So if I have to somehow use the inductive hypothesis to find the matching, what should I do? What do I need to know about the graph?
Check the condition on other subsets of U minus X.
Right. So the question is, does F2 satisfy Hall's condition? Okay. So for this, what we need to show is that for every subset of U minus X, so what we want to talk about is a set X prime of the subset of U minus X. We want to ask, what is the relationship between cardinality of X prime, the cardinality of neighborhood of X prime, in what? So what we want to say is, let X prime be this. I want to show that F2 satisfies Hall's condition. So I have to show that this is less than or equal to its neighbors. In what graph? This I want you to fill the subscript. I want to show that F2 satisfies Hall's condition.
In F2.
In F2, right? The neighbors of X prime in F2. So you must remember that its neighbors in G, H may all be different. We have removed certain vertices, so we have to be careful. We're only thinking about the neighbors of X prime in F2. And we want to say that for no matter what subset of U minus X, X prime that you choose, its cardinality will be always less than its neighbors in the graph. So from now on, we just play around with sets. So you sort of forgot that these were graphs. Right? It's just about sets. So now we have two sets, X, X prime, and both are subsets of U. Right? Like complements each other. So what can you say about the cardinality of X union X prime? I want to estimate the, remember I want to estimate the cardinality of X prime. I know that x and x prime are subsets of U. First, let's ask what is x intersection x prime? What is that?
Five.
Empty set, right? Because x prime is defined as a subset of U minus x. So this, you can just write it as x plus x prime. What principle is this? So this is by inclusion exclusion, right? Okay. So now I know that G satisfies Hall's condition. So if I look at the set, X union X prime, its cardinality, it's less than or equal to the neighbors of X union X prime in what graph? Again, I want you to fill this subscript. I'm not sure if F2 satisfies Hall's condition, but I know that G satisfies Hall's condition.
In G.
In G, right? Okay. So now what we have is the cardinality of X plus the cardinality of X prime is less than or equal to the neighbors of X union X prime in G. This is really what only Halls could have thought of, right? Just playing around with cardinalities. The kind of sets that we saw, inclusion, exclusion, just basic set theory. Okay, so now what we want to do is the following. Right? We want to understand what this right-hand side is. What is it? So we have the set X, we have the set X prime, and we have the neighbors. All right. So both the intersections are empty, we know that. But it could be that X prime has some neighbors in G that are neighbors of those in X also. So they could have common neighbors. Like for example, this is X, this is X prime. They could have things like this, right? That is possible. You just know that these two sets are disjoint. So this is X prime. This is in one partition. This portion. Right? So they could have common neighbors. So this, someone have a question? Okay. So if you look at this, neighbors of X anyway you count. Right? In neighbors of X union X. So what are we trying to estimate? This portion. What are the neighbors of X union X? So neighbors of X, first let me count that. So I've already counted a few of them. Now what should I add to this? So I want to count how many neighbors are there for this set X prime. And I should avoid overcounting. So what should I subtract? Neighbors of X prime in the graph G. So if you look at this particular vertex, right, this I would have already counted in NG of X. So this I should not count, right? So I must count in this portion neighbors here. I must be able to count the neighbors of X in G prime that are not neighbors of X. Is this clear? This should be like really clear. Otherwise, we can go over it again. I'm just trying to, I have to estimate this size, the set of this, the size of this set, and just looking at those neighbors of X first. And then in the remaining, I should discount whatever I've already counted if there are common neighbors. Okay? So now this thing, can somebody fill? What should this be? So this is exactly neighbors of the set X prime. Okay? But in what graph?
F2.
In F2, right? Because in F2, if you remember, we removed the neighbors of X. Is this clear to everybody? Why this term here is neighbors of X prime and F2? If it's not, we will take a look at it. Now things are all like super clear in place, right? So you have X plus X prime is less than or equal to. It gives you somewhat this feeling you actually forgot about graphs, right? You're only looking at sets. Now what can you do? You have this equation. And you have these two terms. Now what are these two terms? Here you know that these two terms are actually equal. Right? So you can just set that. You get that the cardinality of x prime is less than or equal to the cardinality of the neighbors in the graph. We really did not care what set x prime you chose, right? X prime was some subset of u minus x. So for every subset of u minus x, x prime, this condition is satisfied. So what does that mean?
F2 satisfies Gauss condition.
So we have that F2 satisfies Gauss condition. So you know that this is a subgraph. This was the smaller partition was u minus x, and it also satisfies Gauss condition. So you can use the inductor hypothesis. So you can find a matching. Let's call this matching M2, right? That covers or saturates every vertex in its smaller partition. So what is the smaller partition here? Is u minus the set x, right? We showed that this one was the smaller partition. So it saturates every vertex in u minus x. So now what do you have? So you have this u. You have the set x here. You have the set u minus x. And there was the set w. So this is mg of x. There are things like this. There might also be some pattern. This is w minus mg of the set x. So you must remember one thing, that the moment we realize that h does not satisfy Hall's condition here, right? This is what caused confusion last time. The moment you realize h does not satisfy Hall's condition, you forget about the graph h. The only information you have is there is this bitness set, right? There is a set x that witnesses the fact that h does not satisfy Hall's condition. So you have to use this set to find a match. So what you are essentially doing is first match things in this set and match the things in the remaining set separate. So here there will be other edges. Many things like that you don't get. So now I have a matching M1 here that saturates the set X, and I have a matching M2 here that saturates the vertices in U minus X. So what should I do to get a matching M that saturates all of you? These two I got from inductive hypothesis, M1 and M2. So this is a set of edges, right? M1 is a set of edges, these ones, and then M2 is also a set of edges. M1 covers X and M2 covers U minus X. So what is the matching M that covers all of you? It's the set M1 union M2, right? So you just put together both the matches, like paste the two matches and you get a match. So the observation is that the edges in M1 and M2 are vertex disjoint. Can someone see why this is true? So first of all, what is a matching? First, it should saturate every vertex in it, right? When we talk about perfect matches. So Hall's theorem is only about perfect matches. So we want to saturate every vertex in U, which is done by M1 union M2. Agreed. But then we must also argue that if you look at any two edges in M1 union M2, they must never share a vertex. Otherwise, it's not a match, right? Why is this true? So M1 was a matching in the graph F1 and M2 was a matching in the graph F2. So you can recall that F1 and F2, the way we constructed them, they are themselves vertex disjoint. So let's look at the graph F2 here, right? So this is U minus X, W minus NG of X. And if you look at the graph F1 here, right? This is X and NG of X. So because these are matchings on graphs that are vertex disjoint, their edges, the edges from M1 and M1 union M2 can never be vertex, can never share a vertex. So this is indeed a matching. So M1 union M2 is a matching in G that saturates every vertex in the smaller vertex. So in the end, what this tells us is a bipartite graph has a perfect matching if and only if it satisfies Hall's condition. There is also a version of the same theorem for general graphs. It's called touch theorem, but that is something we will not see in this course. It is slightly advanced. But if you are interested, you can take a look at it. So here we crucially use the fact that the graph is bipartite. So now we have if the graph is not necessarily a bipartite graph, then how do you find a necessary and sufficient condition for that graph to have a matching? Right? So if there are any questions about the proof, we can see. Are there any questions? So there are some exercises that you can try to solve. Some problems that can be solved using Hall's theorem. I just want to post like one exercise just to give you a feel that these problems can actually be solved using Hall's theorem, though they don't look like graph theory questions. Right? I will write down the question here, and then you can try to solve it as a homework. Right? Let's say that M people are chosen as prize winners in some competition. And each winner can choose a prize and select two prizes from a collection that has several prizes. So if there are, so every person gives a preference, right? I like this price, I like this price, and so on. So it's not necessary everybody should like all the prices in the bag. Sure. If there are two win prices that every winner wants, so every winner like, says I like this price, 2M such prices. If this is the case, then I want to say that every winner can actually select a price, two prices from the bag. Then every winner is able to select two prices that they want. So first you must formulate this question as a graph theory question. So you must write what the graph is, what the two partitions are, and then you draw an edge between the two partitions. And then use Hall's theorem to show that you can always find, so every winner, so that's one partition, right? Every winner can always find two prices that they want. If there are two M prices. Okay. So this is some question that you may not have thought is a graph theory question. It looks like a counting question, but you can actually use Hall's theorem to solve this. Similarly, the marriage problem that we saw, right, that has several variations that can be solved using Hall's theorem. So these kinds of questions you will get in exams where you have to apply Hall's theorem. So you have to formulate the given question as in the language of graphs and then use Hall's theorem. Then it will just be a straightforward application of Hall's theorem. The moment you define the bipartite graph, the two partitions, one of them is the smaller partition, you can just apply Hall's theorem. Say that there exists a matching and the matching is exactly the answer that we want. So there are more questions in Kenneth Rosen. There are like several textbooks that have like really nice applications of Hall's theorem. One of them is also Latin square. So if you're just interested to know some applications, one of them is Latin square. These are slightly advanced, but still it's good to know that these things exist. So you can probably search for that. Okay, so with that, I will stop if there are no questions. Partha will discuss about trees. If there are any questions about Hall's theorem, you can ask. Okay, and maybe I will just stop sharing.
Okay, so will you continue recording?
Yes, yes, yeah. Let's just make it one record.
Is the screen visible?
Yes, yes.
So after this lectures on matching, we jump onto trees. We'll start with a few basic things and then we'll do a few more interesting things. So probably you have an introduction to trees in some other course. Let me know quickly if you have. Any of you can tell whether these trees are introduced.
Programming.
Advanced programming. Okay, so
Binary trees.
binary trees are introduced. So you are familiar with the definition, basic properties, these things. Okay, we'll quickly refresh it. And then, Vijayan, you are laughing. Why? You are not introduced to trees?
No. Okay, sorry. Yeah.
Okay, no problem. Yeah. So let's some definition and basics. So let me just straight away write the first theorem. Yeah, not everything will be basics. I'll start with some very simple things and then I'll go to some more advanced. So all the graphs I considered in these lectures are undirected. So it's a G is connected undirected simple graph. Simple graph means there is no self loops. That means there is this kind of things are not there. Simple graph on n vertices, let's say. Then the following are equivalent. So this TFE is used for the following are equivalent. G is minimally connected. To G does not have any cycle. So what is minimally connected? If you delete, if you remove any edge, it will split, the graph will split into components. And this is the definition of minimally connected. And also, like any graph satisfies, that's the definition, satisfies the equivalent conditions. This is the definition, equivalent condition of the theorem is tree. That's the definition of tree. So let's quickly prove that. Proof of the theorem. Yes. So the trees, I have given like an, I started with a more like an abstract definition from your course of whatever course you have done. You have perhaps this kind of picture already in mind, but I started with a more abstract definition. Okay, so how do you prove? Let's prove 1 implied 2. So G is minimally connected, and D, suppose G as a cycle, let's give it a name C. Okay. And what do I want to prove? Suppose G has a cycle, then I want to prove that this graph is not minimally connected, right? So let AB be any edge in the cycle C. So let's me draw a picture. AB cycle C. And we delete the edge. Yeah. Now consider any two vertices. What do you want to prove so that it is not minimally connected? That's the contradiction I want to bring, right? That means you give me any two vertex, I'll still exhibit a path between them, even after deletion of that edge A, right? Then it will violate the condition that it is minimally connected. If there is a path avoiding the edge AB, then it doesn't matter. Doesn't matter means whether you have removed or not removed. Otherwise, AB is sitting here, but then you can take the other arc of AB. It's simple argument and complete. Probably you already know this kind of basic things from your other course. Okay, so this is really simple. And now let us immediately prove that 2 imply 1. It's again very simple. In fact, we'll just prove it contrapositive. If you are struggling or something is not clear, stop me, because I just assume that you already have these kind of ideas in your mind from this programming course, and I'm just collecting these ideas. So let's prove the contrapositive. So let's try to prove that not of 1 imply not of 2. That means if let the graph is not minimally connected. That means there is an edge AB. There exists edge AB is deletion still keeps the graph. But then it's very simple, like A and B you delete, then A and B must be connected by some other path, not having AB, and that gives a cycle. Yeah. So it's quite simple. And this is the definition that these graphs are called trees. Now you can match whatever tree introduction you got from your other courses, programming courses. Okay, so let me just list out a few absolutely basic properties of trees. Properties. Let me just list out. Connected graph. Tree if and only if between any pair vertices. Here is exactly one. So the picture that you keep in mind is a running picture. That of course is true, but you can prove it abstractly also. How do you prove it?
Excuse me, sir.
Yes, yes.
Sir, can you please scroll up a bit?
More?
Yes, sir, it's fine. It's fine. Thank you, sir.
I'm just going a little fast probably. I thought most of you probably have these concepts from your programming language course. Yeah. So how do you prove this thing? So for example, that suppose the graph is a tree, but there exists pair X and Y that has multiple paths, right? So from this path, you have to basically manufacture a cycle, right? So let's say this is the path.
It's the union.
Yeah, symmetric difference, right? Someone said union. Is it union or symmetric difference? So let's say this is
Just
one path.
consider the path here.
Yes, and then it could be like this. If I try to draw these pictures, these blocks are coming. I don't know how.
So, I mean,
Not
if
able to
X to
remove
Y
this.
have any greater than one path, then just go from Y to X, then again choose a different path to come to Y.
Yeah. So this is a picture I drew, right? So this
Oh.
this blue path. Whenever I'm trying to draw, some extra boxes are coming in my drawing. So this is let's say the path. So this is the symmetric difference, right? Can you see that symmetric differences? This is let's say the different one.
Can you just write that symmetric difference set expression?
Yes, let me just write symmetric difference is a union of cycle. Symmetric difference of two set means that has inside A but not in B, union that has B not in A. There is a variety of way to see this thing, in fact. And the other direction is also very simple. I just leave it as an exercise. It's very simple. Okay, so far we know that they are minimally connected, equivalently no cycle, and between two pair of vertex there is a unique path. All such thing is true with your basic running example. Yeah, so let me just list down another property too. There are many properties. I just picked up few properties. So every tree on n vertices, let's say n more than equal to 2, has 2 vertices of degree equal to 1. Can someone quickly give, when I say 2, I mean like at least 2. So what is the argument? Particularly people who are trying trees for the first time, they should try it out. It is not that you have seen it first time, you have seen it in programming, but you should try to give this argument quickly.
So if there's less than one vertex, then there's at least two vertices.
Okay, I'll give you, yeah, there are multiple ways to say it. I'll just give you a one-line argument. So take a longest path. So this XY is the longest path in that. Then X and Y will be of degree 1. Why? If it is not,
it will be a cycle.
yes, if it is not, you can extend, right? If it is not of degree 1, then, sorry, Aditi, you said something?
Yes, sir, I said otherwise it will be a cycle, or yes.
I mean, otherwise you can keep expanding it, right? Finally, you will. So if this is not a degree 1, then you can extend this path, which is not in the path of the path, and get a longer path. And this process cannot repeat forever. Eventually, you will have 2 vertex collide and have a cycle.
Sir, is the statement like every tree on n vertices has at least 2 vertices?
Yes, that's what I said. Whenever I mean 2, it's at least 2.
Yes, sir. Yes, sir.
It's very simple stuff. I just list it down. So, property 3. Any tree on n vertices has n minus 1 edges. Yeah. So this proof is also trivial, almost very simple. So it's induction on n. So if n equal to 1, you just have one vertex. It's true. Assume it's true for trees on n minus 1 vertices. So let T be a tree on n vertices. We have just now see that just now we noticed. Just now we noticed that T has at least 2 vertices of degree equal to 1. Right? So let U be one such vertex. So that means this is a tree, and this is the vertex U, and this is the edge that connects the vertex U. Right? Now remove U from T, we get T prime which is also a tree on n minus 1 vertex. Apply IH induction hypothesis. T prime has n minus 2 edges. So T equal to T prime union that edge E. Hence the number of edges in T is exactly this. It's very simple. So let's list down properties. So what is a forest, by the way? Anybody knows what is a forest? Forest, as we simply imagine, forest is a collection of trees. Forest is a collection of trees. Means
So graph with connected components, trees, that is forest.
yes. Yeah, that connected component I just loosely written collection of trees. Now observe the simple property like let F be a forest on n vertices with k components. These are the components. Then F has n minus k edges. Proof is really elementary again. Right? So what is F? F is disjoint union of these components. This dot means disjoint union. So this is a tree on n1 vertex. This is a tree on n2 vertex. A tree on nk vertex. So then the number of edges in F is the summation of number of edges in Ti, I equal to 1 to k. But that's simply I equal to 1 to k ni minus 1. That's just n minus k. Since n equal to summation of. That's it. So these are the listed out of absolutely basic properties of trees that probably you already knew from other courses. I just refreshed it quickly. I didn't take, I think I took just 10 minutes, 15 minutes. Okay, so now let's come back to one at least. I'll be back in a minute. Switch on. Okay, the study of trees actually is very old. I mean, I'll tell you a theorem, a remarkable theorem, in fact. So basically, theme of the next part of the lecture is the counting trees. Counting trees. What do I mean by counting trees? I will give you a set of vertices. 1 to n. The basic question that I want to address: how many trees? Soham, I guess there is a misunderstanding. So he's saying there is a misunderstanding. We did trees in the programming just to create a binary trees from some data, including a data in the tree, deleting a data that. Okay, so I didn't know that. So is that the Soham, is the listed out properties looks too difficult for you to follow? I wrote it down very simple properties. Has anybody felt these properties are tough to follow? Feel free to tell.
No, sir.
I thought these are absolutely simple properties to follow. Soham, you can feel free to say if you have any comment. So counting trees. So the main question that mathematician addressed long time back historically, I give you a vertices 1 to n. So how many trees we can construct on those vertices? So let me remind you a few things. What do I mean by this question? First of all, some of you may have this notion of isomorphism that we have not defined yet in the course. People who doesn't know isomorphism, doesn't matter. People who has this word isomorphism in this head, this question is not about non-isomorphic trees. We are just counting the labeled trees. For example, let me give an example. Let's take n equal to 3. So the number of the different trees that I consider 1, 2, 3, 2, 1, 3, 3, 1, 2. That means, and you don't consider 3, you just don't, when you include 3, 1, 2, you don't again include 3, 2, 1. There is a no left child, right child distinguish. Okay. We don't distinguish it that way. All 2 trees are same when there are edges, labeled edges are same. Is it clear? So our notion of sameness is 2 trees are same when their edge label are same. So there should not be any confusion like, oh, shall I include this picture also in my list if I already included 3, 1, 2? No, that's not the case. So remember. Is that clear? What I mean by different trees on my vertices?
Yes, sir.
Okay. So can I go a little extra, like till 6:30, for example? I wanted to cover it, but I think there is only around 10 minutes left.
Yes, sir, that's fine.
Okay. So the theorem that I go into the story I'm going to tell you is a remarkable theorem proved by Kelly, who was a group theorist, and the theorem was proved in 1889. So Kelly proved the following remarkable result: the number of trees on n vertices are n power n minus 2. It's quite remarkable. Those days, like Kelly was a group theorist and he used to prove result in graph theory. Today, you don't see that. It has become so specialized. Okay, so this is a really old theorem. And this theorem has, as far as I know, at least 6 different proofs. Could be more. It's very celebrated. Kelly has several theorems, but this is one of his celebrated results. So what I plan is to tell you a proof, this theorem, but among many proofs, I picked up a proof that is an algebraic. There are proofs using purely graph theory, purely combinatorics, counting, setting up bijections, but I picked up a proof that's very algebraic. The reason is that firstly, it is beautiful if you want algebra, and second, this proof fix the groundwork for more interesting things in trees that one can prove. It's a remarkable proof, and also this proof is a baby version of the current very active area of combinatorics that's called polynomial methods. But I will not do any advanced thing. We will do only basic things. But it is amazing that even in those days, people found a proof idea using algebra that today people have discovered like a whole branch of combinatorics. That's called polynomial methods. This is a branch of combinatorics which is very, very active even today, with lots of new discoveries and solving many open problems, not just into combinatorics, into different other branches of mathematics. Very powerful methods called polynomial methods. So this is one of the oldest examples of polynomial methods as far as story goes. So let's just take it easy. I mean, there is nothing big hammer we are going to use. Let's start with some really basic thing. If we cannot finish it, we will finish it in next class. So in school, we just study univariate polynomial, right? So what are they? So they look like one variate. Our favorite polynomial is, sorry, so this is a univariate polynomial, and also we have studied bivariate polynomial, right? So let me maybe bivariate, right? F of xy would be our favorite polynomial. These are the school examples that we have studied. But polynomials need not to be only univariate and bivariate, right? They could be multivariate, right? For example, you can have n variable, x1, x2. Have you seen these multivariate polynomials in any of your algebra course? In any situation? Have you encountered them, played with them?
I don't think.
Okay. There's nothing fancy about it. Instead of having 2 variables, you can have n variables. For example, a 3 variable polynomial could look like x1, x2, x3. It could look like maybe x cubed plus 3x1 squared, x2, x3 plus 4x1, x2, x3, and so on. You can keep on adding terms. And this is nothing stops you from defining a polynomial over n variable. And when you grow up, you'll see that these objects are everywhere in mathematics. Whatever branch of mathematics you study in future, these multivariate polynomials are the building blocks of mathematics, starting from geometry, combinatorics, algebra, everywhere. Okay, so in general, they look like x1, x2, maybe xn. I cannot write them, but maybe they will look like x1 power n, or x1 power some number d plus. Okay, I don't need to write.
We actually came across during multinomial theorem in some probability courses.
Oh, right. So you have come across the word. So but nobody said it. So I thought you just. So these are the multivariate polynomials, and the coefficients. These coefficients, like these are the coefficients, right? 3, 4. These coefficients could come from anywhere. It could come from reals. It could come from rationals. It could come from complex numbers. It could come from finite fields also, but we don't care about that at the moment. It could be just integer also. According to our choice, we can give them the coefficient. Any question about this multivariate polynomial business? Feel free to ask. This is a new kind of proof idea I'm going to introduce today. If you are confused about any basic definition, you tell me. So there are a few basic definition, like monomial. Each term in a multivariate polynomial. What is your favorite multivariate polynomial? Anybody has any favorite multivariate polynomial? Is a monomial. For example, consider these polynomials. So these terms, they are called monomial. These terms are called just a name. They are given the name monomial. So this is one point. Point two, the degree of a monomial is the total degree. For example, if the monomial is x squared x2 x3, the degree is 2 plus 1 plus 1. The x1 degree is 2, x2 degree is 1, x3 degree is 1, it's 4. So degree of a multivariate polynomial is the maximum degree over its monomials. By the way, I went the basics of tree bit fast, but you can always go back and look at it. And if it's not something clear, ask me next class, because I planned and then I could not accommodate that, so I just went little fast on the very basics of trees. But these I'm going more slow, right? So degree of a multivariate polynomial is a maximum degree over its monomials. Makes sense, right? For example, in the school, when you look at this univariate polynomial, you will call it degree 2 because that is the highest degree. That notion generalizes to multivariate setting also. A multivariate polynomial,
the number of monomials in a polynomial of degree n, that is the partition number.
right?
Partition of it.
Yes. Good point. The multivariate polynomial is homogeneous is a definition. If the degree of each monomial is same. For example, our favorite polynomial it's homogeneous of degree 2. See, degree 2 xy total degree 2 degree 2. Okay. Let me know that any doubt you have on these questions, on this this setting of multivariate polynomial. We have not gone into Kelly's theorem at all. I'm just describing some really basic algebra. I'll take maybe another 15 minutes and then stop, and the rest we'll do in the next class. But let me know whether you are confused about the multivariate polynomial notion itself. Feel free to ask any question. Any question? Is it clear? Everybody understood?
Yes, sir.
Okay, good. So now let's attack the Kelly's proof. Okay. So the set of vertices on which we are going to count the trees. Set of vertices 1, 2. So the remarkable insight that he has is that associate the variables x1, x2, xn to the vertices 1, 2, n. What do I mean by association? Let's take an example. Let's take our first example 1, 2, 3. the basics. Remember that Kelly was a group theorist. He was an algebraist. So it's not surprising that he used to think things in terms of algebra rather than combinatorics. So take for example this tree. Okay. So I will identify this vertex 1 with my favorite variable x1. Identify it 2 with the variable x2. What do I mean by identify? I am coming to that. 3 by x3. Now, whenever there is an edge ij, yeah, I will associate this product xi xj with it. For example, if I have this tree, I can have a nice association with it in the following thing. This is an edge, right? 1, 2 is an edge. 1, 2 is an edge. For this edge, write the variable x1, x2. 1, 3 is an edge. Write the variable x1, x3. Basically, what you got, x1 squared, x2, x3. So if this tree, I give it a name T, I got a monomial MT is a monomial corresponding to T. So did you understand, given a tree, how do you construct a monomial? Transforming graph theory to algebra.
Or so we could just say that it is the, say, x1 raised to the degree of 1.
Right, I'm just going to say that, yeah. Right. What Aditi said, I'm just going to repeat. In other words, MT is x1 power degree of x1, x2 degree of x2, xn. That means every tree, given a tree, I can associate this monomial with it. Which is same as product. So as Aditi said, I just wrote it. See, the degree of x1 is 2. And degree of x2 and x3 are 1, 1. They are leaf, right? And so this is also same as xi, xj. ij is an edge of the tree. Is it clear to all of you? If anybody has any doubt, let me know. So that the remarkable identity.
From here, the multinomials here then in power -1, putting all equal to 1, and
Say it
by
again.
n because we don't care about the.
Sorry, I didn't hear you properly. Can you repeat it? What you said?
Yeah, so from we considered all the terms of x1 plus x2 dot 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 xn whole power n-1 because n-1 edges are there in this tree, and now put x1 equal to 1, x2 equal to 1 because we want to count all the sum of the coefficients of this on the right hand side. And
But
because
all
this is
but the degrees of
combination doesn't matter, so 1 by n. I don't know if that is.
Sorry, what you
I
said?
think
You went too fast.
Yeah,
Maybe you
x1
can.
plus x2 dot 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 xn whole power n-1. We take that multivariate polynomial. The right hand side will give us all the possible trees, right? If we plug in x1 equal to 1, x2 equal to 1, all the xi is 1. Sum of the coefficient of the right hand side.
Why it is n-1 power?
Because number of edges is n-1 in a tree of vertex. n plus 0. So,
It will be 2n minus 2, right?
2n minus 2 is the degree, yeah. So maybe we can talk later the what Journey says.
yes, sure.
Yeah. So the degree of each monomial is 2n minus 2. Why? Because there are exactly n minus 1 edges, and each edge contributes to degree 2. True? Is that what you said just, Aditi? That was your time to say the degree of each monomial is 2n minus 2, right?
Yes, sir.
Okay. Right. So the remarkable identity that Kelly established is that he said, okay, let us write this expression C of x1 to xn, which is summation of all possible trees. And this is equal to x1 times x2 times xn times x1 plus x2 dot 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 xn power n minus 2. This is for n greater than equal to. This is the remarkable identity that Kelly proved. Basically, he says that, okay, so I do not know how many trees are there, but abstractly write all the monomials of the trees. So I get and add them here. You got a big polynomial. That polynomial is nothing but in other form. This polynomial can be written in a much nicer mathematical form. That is just this.
Does a monomial uniquely determine a tree?
Good question. So what do you think?
I think it does not, sir.
Yes, sir. I also don't think so.
But here the point is that I count all the label trees, right? So it is only that if the edges are different, my trees are different. Yes. So if that is the case, then I will count it twice, right? One monomial will come twice. That's what your question. See, this is just an identity. So I am not saying that these T's are MTs are different.
Yes, sir.
Right? Does that answer your question?
Yes, sir.
So whatever be that T comes from a monomial, so that all these collections are here. And as a whole, this polynomial is equal to this polynomial. Okay. So we don't have time to prove it, but let's check a basic case. And once you prove that, then how do you prove Kelly's theorem? That means if suppose this identity is true and put xi equal to 1 for all I, then the left hand side will be what? Every monomial refers to one tree in your count, right? So this is exactly the number that you are looking for. And here it will be n power n minus 2. Because it's an identity. If you put xi is equal to 1 left hand side, you have to put xi equal to 1 in the right hand side also. Right? Did you get the point?
So I
So
didn't understand.
I still don't see how we like one monomial may represent two different trees, right? For example,
Can you give me an example? Yeah, let's take an example.
yes. So for example, x1 squared, x2 squared, x3, x4
X1 squared, X2
squared,
mhm,
x3, x4. So
yeah.
yes, sir. So x1 and x2 will have to be connected, and in this, we don't know whether x3 and x1 like
So tell me,
x3.
yeah, give me the explicit trees. I'll explain your question.
So
one.
it's
So this is a vertex 1, 1, 2. I guess you have this in mind, right? 3.
yes, sir, and 4 connected to 3, and then we swap 3 and 1.
1 minute. 2. You have to make.
Sorry, 2, 1, 3, 4. Okay, sorry, 3, 1, 2, 4. Yeah.
And what is the other trees?
We swap 1 and 2.
1. Sorry, what did you?
1 will be connected to 4 and 2.
4 and 2. And 2 will be connected to 3.
Yes.
That's what you said, right?
Yes. Sir.
Yeah. So now I explain. So this is, you are right, what you are saying. There could be multiple such examples. And as I said that these two trees are different. But the point is that then these monomials will be counted how many times in the left hand side? Twice, at least, right? Because I am writing this monomial empty for every possible trees. And finally, I am interested only count. So this monomial will come with a 2 in front of it. Because there will be 2 repetition.
Yes, so when we multiply the edges, like when we do that, we will get this. But
So
I
let's draw. Let's try to understand. So here, what will be the case? X1, X2, X2, X4, X1, X3, right? So this is X1 squared. I just illustrating it for everybody. Here also you will have this order: X1, X4, X1, X2, X2, X3. Just to make sure, this is X1 squared, X2 squared, X3, X4. These two trees are different, fine. But the point is that then this monomial will appear multiple times in the sum. And when you put xi equal to 1, that multiple value will come up.
Oh, yes. Okay, sir. Yes.
Right? So it does not matter.
Yes, sir. I'm just confused.
Got it?
Yes, sir.
Right. Good. Everybody got that question that Aditi asked? That point? Okay, so let's check something with one more check. I'll conclude today's class. Let's check n equal to 1 case. Obviously, this number of trees is only 1. So now we have x1. What you have in the left hand side? Left hand side is obviously x1, right? What do you have in the right hand side? Sorry, left hand side is x1 power 0, because that's the degree of this tree is 0. There is no degree, no age here. So left hand side is x1 power 0 equal to 1. What is the right hand side? It's not a polynomial, but function wise it will match. So you will have x1, and then you will have a x1 power 1 minus 2, that is minus 1, which is also 1. Interestingly, it matched even in the division case, but usually it is stated from n greater than 2, because the base case is obviously true for Kelly's theorem. If n equal to 1, you have only 1. So we'll prove this identity in the next class. Any other doubt? Okay, so if you do not have any doubt, then we will go. Otherwise, you can ask question. Maybe the recording can be stopped now.
Thank you.
Recording stopped.
Thank you, sir.
Thank you.